At this juncture in the course, we begin to shift our focus towards the chemistry of the carbonyl group. The carbonyl group is an incredibly important group in organic chemistry, and we will see the biological applications of it in a few minutes. Just to refresh your memory, a carbonyl group has a carbon-oxygen double bond. So depicted on the screen are two of the subclassifications within carbonyl groups, namely aldehydes and ketones. So an aldehyde is when one of the atoms bound to the carbonyl carbon is a hydrogen atom, and a ketone is when both atoms bound to the carbonyl carbon are carbon atoms. So carbonyl compounds, as I've said, are present in many biological molecules, and what I want to do is give you some examples of this. So first of all, amino acids contain the carboxylic acid functional group, which is one example of a kind of carbonyl group. So proteins are formed when the carboxyl end of one amino acid reacts with the amino end of another amino acid to give an amide. And a polypeptide or a protein are just lots of amino acids linked together through these amide bonds. Okay, so carboxylic acids and amides are two more examples of carbonyl groups that show up in proteins. Free carboxylic acids also show up on the side chains of two of the naturally occurring amino acids, aspartic acid and glutamic acid. Carbohydrates, another major class of biological macromolecules, are built out of smaller units called sugars. And sugars, by definition, are polyhydroxyaldehydes or ketones. What that means is that they are molecules, they are frequently 6 carbons, although there are also 3 carbon, 4 carbon, and 5 carbon sugars that are important, in which there is a carbonyl group on one carbon, and all of the other carbons that are not carbonyl groups have OHs on them. So for example, the structure of glucose, this is called an aldose. It's a sugar that is derived from an aldehyde. And as you can see, one end of the chain in its open chain form contains an aldehyde, and every other carbon that is not the carbonyl carbon has an OH on it. Fructose is a type of sugar called a ketose, meaning that is derived from a ketone. And as you can see, the carbonyl group on fructose is a ketone. It's got a carbon on one side above it, a carbon on the other side below it, and once again, just like in the case of glucose, every carbon that is not part of a carbonyl group has an OH on it. Lipids, another class of biological molecules, are most typically found in the body as triglycerides. And what triglycerides are they are the triester that is formed between glycerol, glycerol is shown at the right, that is a 3-carbon triol or trialcohol, and the ester is formed between glycerol and 3 what are called fatty acids. Fatty acids are simply long-chain carboxylic acids, and in this case, the carboxylic acids have 10 carbons. In many carboxylic acids, fatty acids in your body, the carboxylic acid chain is actually longer, frequently has 16 or 18 carbons. So once again, free fatty acids have the carboxylic acid functional group, and esters are formed when the acids condense with a molecule of glycerol. So for the purposes of this course, I classify carbonyl groups into 2 broad classes. So, and I'm classifying them this way based on how they react. So the carbonyl functional groups that I'm putting in class 1 are just the aldehydes and ketones, And then the carbonyl functional groups that I'm putting in class 2 are the carboxylic acids and their derivatives, such as acid chlorides, anhydrides, esters, and amides. So the class 1, the aldehydes and ketones, the way they react is to just undergo nucleophilic addition at the carbonyl group. The class 2 carbonyl compounds have the carbonyl carbon actually in a higher oxidation state, and one of the groups bound to the carbonyl carbon is capable of being a leaving group. Therefore, their characteristic mode of reactivity begins the same with nucleophiles adding to the carbonyl carbon, but then after that happens, you actually eliminate the leaving group, you kick out the leaving group, and regenerate the carbonyl group. Okay, so we will have a lot to say about both of these classes of molecules in the next several videos, but this current unit is going to focus on the class 1 carbonyl reactions, and then the next unit will focus on the class 2 carbonyl reactions. Okay, so you've already learned, if you've been following through these videos, about a class 1 carbonyl reaction, and that is the reduction of aldehydes and ketones with sodium borohydride. So you should recall that if an aldehyde is reacted with sodium borohydride and ethanol, the product is a primary alcohol, and if a ketone is reacted with sodium borohydride and ethanol, the reaction is a secondary alcohol. We introduced this in the concept of organic oxidation and reduction reactions in order to understand oxidation states and what's going on with them. Now we start as our launching point into carbonyl chemistry by looking at this reaction from the perspective of what's happening at the carbonyl group. And if you look at the mechanism and look at the simplified version of the key step of the mechanism, sodium borohydride is a source of H-. So H-, of course, is the nucleophilic form of hydrogen, and the carbonyl carbon is electrophilic, which means it will react with a nucleophile, and specifically with the lone pairs of that nucleophile. So we draw an arrow from the lone pair on the hydrogen to the carbonyl carbon, and the reason the carbonyl carbon is electrophilic is because you can break the CO pi bond. Remember that pi bonds are easier to break than sigma bonds are, and in this case, when you break the pi bond, you put the minus charge onto the oxygen atom. This then, in the actual reaction, picks up a proton from the solvent to generate a neutral product. But in the key step, H-, which is a very strong base, reacts, and the intermediate that is formed from that reaction step of the reaction has a minus charge on the oxygen and is not as strong of a base as H-. So in the next video, we're going to start to consider this reaction in the context of the reactions we're going to learn in this unit, and discuss the fact that while the sodium borohydride reaction is essentially irreversible, many other carbonyl addition reactions are actually reversible.